Hello, folks. Welcome to Lecture 34, where we will talk about beats and something called a Doppler effect. Now, let's talk about beats first. Now, we have always talked about when studying interference that waves of the same frequencies, when they talk to each other, what happens? Either we have constructive or destructive interference, right? Constructive is when the waves are amplified, while destructive is when the waves are diminished. Constructive interference occurs for places where waves add to get higher amplitude, in other words, and destructive interference where amplitude is decreased because the waves are out of line, and the opposite is true for constructive interference. What happens when waves of different frequencies interfere? We haven't talked about that. Well, let's look at it. Let's say we have two waves traveling with frequency f1 and f2, and f1 is clearly not equal to f2 because, as you can see, for the same amount of time, the wave shapes produced are different because the number of waves produced in the same amount of time for f2 is higher than f1. Alright. Now we notice that in some places the waves are lined up. For example, in this position, both of the waves give us crests. So these would be places of constructive interference, right? So they will add each other and increase the overall amplitude. However, I have made a mistake there. I was going for something like that. Okay, so that the trough of a wave is lined up with a crest of another wave. Forget about this lower part. In these places we will have destructive interference, right? And the waves will try and cancel each other out, or at least diminish their amplitudes. The resulting waves of this kind of interference of two waves with different frequency looks like this. It's a very rough sketch, but we can see that it is a combination of constructive interferences and destructive interferences where the amplitudes are diminished and places where amplitudes are amplified, actually. Alright, so this is a phenomenon where places like high amplitudes you will hear very loud sounds, but places of lesser amplitudes you will hear quieter sound. Alright, this phenomenon where the sound you hear goes from loud to soft to loud again, this is basically what we mean when we talk about beats. Okay, this is what beat is all about, the phenomenon of sounds going from loud to soft to loud. Alright, and we can define a beat frequency, call it f beat, and that is given to us as the absolute value of the difference between the two frequencies two interfering waves with their different frequencies. So absolute value of f1 minus f2. Alright, because absolute value, because it doesn't really matter which one is greater. What matters is we get an overall positive value. Okay, now to test our understanding of this, let's look at an example. Alright, so here we have a C note in a piano string which has a frequency given to us to be 261.6 Hertz. And now to tune, say, this piano to this particular note, we place a tuning fork at that note or the C string, resulting in 4 beats per second. Alright, so clearly we have the beat frequency here, f beat, and we have one of the frequencies given to us. Let's say this is f1. Alright, and we want to know what are the possible frequencies that the string can have. So the word possible here is important, and we will soon know why there are multiple frequencies that are possible for that particular string when it's oscillating at 4 beats per second. Okay, now we learned that we know the relation between the beat frequency and the two waves or two frequencies interfering with each other. Here the frequency of the tuning fork and the frequency of the C string. Then F1 minus F2 is equal to the absolute value of F1 minus F2 is basically the beat frequencies. Alright. So therefore, what is the meaning of this absolute value? Well, what that means, according to this equation, we have 4 beats per second, which is the beat frequency, and that is equal to F1 is the C note frequency, 261.6 Hertz, and we yet don't know what the other frequencies might be, what F2 might be. Now at F2 it says that there are a number of possibilities. Why? Because of this absolute value right here. What this absolute value means, as we know that absolute value of a number, say 1, is equal to 1, or absolute value of a number minus 1 is also equal to 1. What this basically means is that whatever is in here, we turn the absolute value turns it to positive. Okay? Alright. So the absolute value of this difference being 4 technically means two things. Either you get the original number, similar to if you took absolute value of 1, you get 1. Similar to that, if you took out the absolute value from the equation, you will get that this difference can be exactly positive 4. Okay. However, without the absolute value, it could also be negative 4, because the absolute value basically forces things to be positive, right? So if without the absolute value, this equation can also be a negative 4. Therefore, we get two possible frequencies. In this case, we will get a frequency if you subtract 4, if you change sides for F2 and 4 and solve for F2, you will get here 257.6 Hertz. Alright, one of the possible frequencies. And in this case, you will get a resulting frequency of 265.6 Hertz. Okay, therefore we have two different frequencies. One is louder and one is quieter. Okay, therefore we again understand that the beat frequency is nothing but the perception of sound going from loud to soft to loud. Alright, so therefore we will have both a louder frequency, that a frequency with a higher pitch, actually not loud. Loud is related to its amplitude, which is also true in this case because you have interference. However, frequency will be two possible values just because of this presence of absolute value sign here. Alright? Okay, let's move on to Doppler effects. To picture a Doppler effect, imagine an ambulance approaching you. You are standing on the sidewalk, you're not going anywhere, you're just standing there, and the ambulance has its siren turned on, and is approaching you. Alright? So, quite clearly, from everyday experiences, you notice that as the ambulance gets closer, you hear a higher pitched sound. Alright, the pitch gets higher, while as it goes away from you, the pitch gets lower. Right? Now let's try and explain the physics of it. Let's understand what happens physically that this is apparently the phenomenon. Well, think about the source of the sound, the siren, and it's emitting wavelengths of sound, right? Let's say this is its original wavelength. Let's call the original wavelength of the sound being produced by the siren let's call it lambda. Now, as it gets closer to you, so you're standing somewhere here, right? As it gets closer to you, the waves get squashed in between you. Okay, that's for a lack of a better term. The waves get closer together as they're squeezed in. Alright, therefore the lambda actually is changing. The lambda, if you remember, is the distance between the wavefronts. So lambda, as the source approaches you, changes or gets smaller and smaller, right? And let's call this lambda 3 prime, and let's call this lambda 4 prime. All right. In this phenomenon, you can clearly see that lambda uh, 1 is lambda is greater than lambda 1 prime, which is greater than lambda 2 prime, which is greater than lambda 3 prime, which is greater than lambda 4 prime, right? So the waves get closer together. Wavelength, it seems to be decreasing as the source moves towards you, okay? If the wavelength is decreasing, we know that v equals f lambda for waves, and frequency is v over lambda. So if the wavelengths get smaller, the frequency get higher. So as the source approaches you, source goes towards you, then frequency goes up, meaning the pitch of the sound goes up. As simple as that. Alright? And as the siren, as the ambulance reaches you, you hear the sound with a greater pitch. Alright? Now mathematically, as we have understood by now that physics is a very mathematics based subject, so we need mathematical equations to really understand what's going on. Now for a time period t, right, for a time period t, what happens to the wave? The source moves towards you, so the waves are actually moving towards you, the wave fronts are moving towards you that are created by the siren. Then in a time period t, the source takes the waves closer to you, a distance of its speed times the time period, right? As simple as that. The distance the source travels is equal to the speed of the source times the time period we're considering. Why is this necessary? Well, this is necessary because if we consider the source to be here and it's producing waves of original wavelength lambda, then as it reaches you and the waves get shorter, this is not a shortened wave, the waves get smaller wavelengths, okay, like that. Let's call this lambda prime. There is a difference, okay, there is a difference of the wavelengths. And what is that difference? Lambda minus lambda prime, because lambda is larger than lambda prime. Lambda minus lambda prime must be equal to the distance the source moved, right? The difference of the sound waves is basically how far the source has traveled in that particular time. So if you plug in what we found for ds, the distance moved by the source, we have this equation. And think about what t is. T is just 1 over frequency, and frequency is v over lambda. So 1 over frequency is lambda over v. And this v is the speed of sound. Okay, and we can just think of it as 343, the speed of sound in air at room temperature. Alright, so if you plug for t, if you plug in lambda over v, we get lambda minus lambda prime equal to vs times lambda over v. Alright, now we can see that there are two lambdas on each side, and we want to find the new wavelength. So we solve for this lambda prime, the new wavelength. Lambda prime is then lambda minus vs over v times lambda, and we can factor lambda out of the equation right here, and we get 1 minus vs over v. Vs is the speed of the source, okay, and in this case it's the speed of the ambulance. Alright, so this is how you get the changed wavelength, the apparently diminished wavelength for the source moving closer to you who is stationary. From wavelength we can also then go ahead and find what the new frequency is. The new frequency is f prime. F prime is equal to v over lambda prime, right? Now v is just the frequency of the speed of sound, again 343, you can think of it like that, and if you solve for only frequency terms here, right, if you want to get rid of this lambda, what we can do, just plug in what we have for lambda prime. So v over lambda prime would be v divided by this whole thing. So v over lambda 1 minus vs over v. Now v over lambda, what is that? V over lambda is frequency. Alright, so if v over lambda prime is f prime, then v over lambda is just f, the frequency of the sound of the source, the original frequency. So f prime, v over lambda is just f, the original frequency of the source, which is the siren of the ambulance, and we get the new frequency in terms of the old frequency or the original frequency to be f times there is already a v in this case multiplied to this whole thing. We have just replaced lambda prime here, right? So if you actually there is no v multiplied. If you take out the v from this denominator, you take the LCM and simplify this whole thing, you get f times v, the speed of sound, over the speed of sound v minus the speed of the source. This is the increased Doppler frequency. Alright, Doppler frequency for the observer standing still while the source moves closer. So this, what we talked about, is the source moving toward an observer. Alright. Okay, so what happens if the opposite thing occurs? Well, when the source is moving away from you, alright? So you're still standing where you were standing on the sidewalk, right? But now the source, the ambulance, is receding. It is moving away from you. It has passed you, alright? When that happens, the ambulance, as it moves away from you, the waves get larger and larger, alright? The wavelengths get more separated from each other, alright? So if this was your wavelength closer to you, this is the newer wave. This is what lambda prime is in this case. The wavelength is getting longer. If the wavelength is lambda prime is greater than this lambda, okay, if the wavelength is getting larger, that means frequency is getting smaller. So as the source moves away, as the ambulance or source moves away, the Doppler shift is the frequency getting smaller, and that results in lower pitch. So you hear the sound get lower and lower and softer and softer as the source moves away. You can carry forward a similar derivation of the previous steps and then find that for a source moving away from the observer, the new frequency is f prime equal to the original frequency of the source moving away times this original frequency is the frequency of this particular source, and times the speed of sound over v plus vs. So we can see that the only difference it is a sign. The minus here becomes a plus there, and lambda prime again is just a difference in sign. The new wavelength in this scenario, when the source moves away, is lambda times 1 plus the source velocity over the sound velocity. Alright? Now the same kind of phenomenon occurs if the observer is moving. Observer is moving, source is at rest. Okay? Source at rest. So the ambulance is stationary, it just has its siren on for some weird reason, and the ambulance is stationary while you are walking towards it, and then away from it. Okay, let's say we have the same ambulance right here, but you have walked past it. Okay, so the same thing actually happens for when you get closer and closer to the source. The waves that are reaching you, sorry, or the wrong kind of wave shown. Now as the waves get closer to you, and actually the waves are, you are moving close to it. As you move closer and closer, the waves get squashed in together. As you move farther away, the waves get more and more separated. Alright, so you can follow along the similar kind of derivations that we have known. In this case, the wavelength gets decreased while the frequency gets increased, so you hear a higher pitched sound. For this scenario, when the source is moving, when the observer, you, are moving towards the source, the frequency is given to us. The new frequency f prime is equal to f times v, the speed of sound, times plus vo. Vo means the velocity, the speed of the observer, over the speed of sound. All right, and the corresponding wavelength, the new wavelength lambda prime, is given to us as the original wavelength lambda times the speed of sound over speed of sound plus speed of observer. All right, O here means observer. Okay, this is for when the observer is moving closer to the source. What happens in the opposite case? Again, there is only a change in sign with the previous case. The new frequency in this case, let's just write down what happens. The wavelength increases, so the frequency decreases as you move away from the source, and therefore you hear a lower pitched sound the more you move away from it. So the new frequency is equal to the old or original frequency times the speed of sound minus the speed of the observer. So just a change in sign over the speed of sound. Similarly, lambda prime is also just a change of sign. Lambda v over v plus vo. All right. So this is when the observer is moving away or receding from the source, the ambulance here. All right. Now let's look at an example to test these very confusing ideas. Let's check out this example where we have a driver sitting in his car, sounding the horn, and the horn has a frequency of 500 hertz. Now the horn noise reflects off of a car moving at 28 meters per second towards the first car. Alright, so let's picture it here. So we have the first car, let's call this car 1. Car 1 is just sitting there, so V1 is just 0, and this guy is just sounding his horn. Alright, so the horn frequency, let's call this the F1, has a frequency of 500 hertz. Alright, this is also this is the source, this is the main source of horn. Alright, now there is a second car that is approaching the first car. Let's call it car 2, approaching the first car at a speed of 28 meters per second. And what happens is the horn noise comes in and then reflects off of the second car as it moves towards the first car. Alright, so the noise gets reflected off like that. Anywho, what then happens is we want to know what is the frequency that the first driver, the stationary driver, hears. Alright, now there are two things happening. First, this guy is sounding the horn, and the waves produced by that horn goes off and hits the second car. Now the second car is an observer in that case, right? In that scenario 1, let's call it 1, car 2 is a moving observer. Alright, because it's not the source, it is getting blasted with horns. So this car 2 is the moving observer moving towards the source, towards the source, which is car 1. Alright. Now for a moving observer which is moving towards the source, we have these formulas, these equations, right? Now we want to find the frequency. Let's do that. What is the frequency? The frequency of a scenario where the observer is moving towards the source is given by f prime equal to the original frequency of the source frequency, times the speed of sound plus the speed of observer over the speed of sound. We know all of these things. The source frequency is 500 Hertz. The speed of sound is 343 at room temperature in air, and the speed of the observer is given to us to be 28. Now these are frequencies, scalar quantities, and when we talk about frequency shifts and Doppler effect and all of that, all of the wave business, we just consider the speed, that is the magnitude of velocity. Okay, we don't need to take care of directions. So that's that over 343. Alright. Therefore, the frequency that reaches car 2 is f prime, which is 541 Hertz. This is what the driver of car 2 hears. Okay, but our goal is to find what the driver of the first car hears. Alright. Now what do we do with this information? Well, now in the second scenario, the waves get reflected off. Of what? Now the waves are reflected off car 2. So the origination of the waves that the stationary driver actually hears comes from car 2. Hence, car 2 now becomes the source. Okay. Car 2 becomes the source, moving toward observer. Moving toward observer, and car 1 is the observer, and it's at rest. Observer at rest. Now for source moving towards observer at rest, the formula for frequency is this one right here, and let's call the new frequency, the frequency that this car hears, let's call it f double prime, and f double prime is equal to the source frequency. Now the source frequency is f prime, remember the car 2 is the source, so f prime times the speed of sound over the speed of sound minus the speed of the source. The source again is car 2. So what is the f prime here? F prime is the speed of the source, in this case car 2, 541, times the speed of sound, 343, over speed of sound minus speed of source. Speed of source is car 2, which is approaching car 1 at 28 meters per second. We get a frequency of 509 Hertz. This is the frequency that the stationary driver sitting in car 1 blasting his horn hears. Alright. I hope this example made the concept of putting Doppler effect into work a little bit more accessible. Thank you very much.